4.1 Related Rates. Before we start, I'm just going to tell you that this is one of those chapters that people often dread. It's all word problems and nobody likes word problems. However, I'm telling you, this is not one of the sections you should dread. If you get down the approach and you understand how to read the problem, these questions are not one of the hardest things that you'll see in this course at all. But they are scary because they're all word problems. We need to learn how to read these questions properly, and then I promise they won't be too bad. So what are related rates, to begin? If two variables are connected by an equation, and at a given moment of time, one of them is changing at a known rate, then using the chain rule, we can find the rate at which the other variable is changing. To solve a problem like this is to relate two rates of change, and that's why it's called a related rates problem. So in order to do all of these problems, we're going to find an equation that relates the quantities and then use the chain rule to differentiate both sides with respect to time. So note, when we're doing related rates, we're differentiating with respect to time. Before, we've always been doing dy dx, differentiating with respect to the x variable. So that is why when we were doing implicit differentiation, we had to remember to multiply by y prime because we had to multiply by the derivative of the baby. Now when we do these problems, we're going to be taking the derivative of some function, let's just call it f for the moment, with respect to time. So this is how we're going to write it. Take the derivative with respect to time. Take the derivative of the f function with respect to the t variable. So the first question we're dealing with says that air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters cubed per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? In these questions, we really want to use units to help us out in the problem because it's going to really tell us a lot. So it's telling us that volume is increasing at a rate of 100 cubic centimeters per second. Right there, we can see that this is a rate of change because we're talking about centimeters cubed per second. And because we have centimeters cubed, we know that's a volume thing because volume is measured in cubic units. So the derivative of the volume with respect to time, and that's how we'll denote that, and we must denote it like that, is 100. I don't write the units when I write out all my information up here, just so I don't have too much to see at the end. I like to just write all my information down here. And the other important piece of information we have is when the diameter is 50 centimeters. How fast is the radius increasing? How fast is it increasing? What is the rate of change of the radius when the diameter equals 50? Alright, so we do need to know the equation for volume. Volume equals 4/3 pi r cubed, and we will review which formulas you need to memorize, so don't worry right now. And then we can't really substitute anything in until we have what we're looking for. We're looking for dv dt. So if I take the derivative with respect to t of both sides of this equation, just like I did in implicit differentiation, we're going to get dv dt equals You can pull the 4/3 pi out because that's a constant. And now, like we were saying before, that when we took the derivative of y, we got y prime because the y had an x inside of it. Well, since the radius is changing over time, when we take the derivative of the radius and we get 3r squared, we must chain that also. And all of these are going to be, the variables are going to be changing over time. So all of them will have a baby inside of it. Now we just plug in the information that we had in the original equation. So we had 100 equals 4/3 pi times 3 times r, and our radius was 50 over 2 squared times dr dt. So we're trying to solve for dr dt. So these cancel out, and the 4 is going to cancel out with this 4. And so we have a 50 squared, and we have a pi over here. So we get dr dt equals 1 over 50, 25 pi. And then the units, how fast is the radius of the balloon increasing? That would be centimeters per second. So it's increasing at a rate of 1 over 25 pi centimeters per second. Example 2 says that a ladder 10 feet long rests against a vertical wall. So let's draw a picture so we know what's going on. A ladder 10 feet long. So this ladder is 10 feet. If the bottom of the ladder slides away from the wall, so the ladder is sliding away from the wall like that, at a rate of 1 foot per second, so it's going that way at 1 foot per second, how fast is the top of the ladder sliding down the wall? So we want to know what this is. And the bottom of the ladder is 6 feet from the wall. So let's call this x, and let's call this y, and let's call this side z. Now we know z is fixed at 10. It's always 10. The x is changing, and ultimately we want to know, they are asking us, how fast is the top of the ladder sliding down the wall? So this would be dy dt, right? And this is dx dt. So we want to know dy dt is what when x is 6. Now we can keep in mind that z equals 10 always. That doesn't change. However, this variable is changing over time. So, what can we set up about this problem? Well, we know that x squared plus y squared equals z squared, right? Because it's a right triangle. The only thing that we know that remains constant is the z. So all we know is x squared plus y squared equals 10 squared. We cannot substitute in for the x because it's changing over time. Let's go ahead and take the derivative of both sides of this equation. So when we take the derivative of x squared, we get 2x times dx dt. Remember that the x is changing over time, so we must take the derivative of the baby. We're taking the derivative with respect to time here, not with respect to x. Similarly, we would get 2y dy dt. Remember, when we take the derivative of the z, since the z is not changing over time, The derivative would just be 0. It's a constant, and the derivative of a constant is 0. So we are left with dy dt equals negative x over y. Now what is x and what is y? Remember, we wanted to find dy dt when x was 6. So now that we solve for dy dt, at this moment we can now insert the values for x and y. So we're saying when x is 6. Well, when x is 6, then we have this triangle. We have 6, we have y, and we have 10. And this would just be our 3, 4, 5 triangle, so we don't really need to solve anything. Y would be 8. So we have negative 6 over 8, or negative 3/4 feet per second. Example 3. A water tank has a shape of an inverted circular cone with base radius 2 meters and height 4 meters. If water is being pumped into the tank at a rate of 2 meters cubed per minute. Dead giveaway there on the units. We have a volume problem and so we know that the derivative of the volume with respect to time is 2. Find the rate at which the water level is rising when the water is 3 meters deep. So what are they asking us? They're telling us we have 2 meters by 4 meters. Find the rate at which the water level is rising. So we're saying dH dt is what, right? When the water is 3 meters deep. When the height is 3. If you can learn how to write this, you will have these problems down. Now the volume of a cone is 1/3 what the cylinder would be, so 1/3 pi r squared h. That would just be the area of the base times the height, and then 1/3 of it for the cone. And we have two variables here. We don't like two variables. We want to cut it down to one, if at all possible. Let's do a little bit of geometry here. Let's look at this right triangle right here. We know that when the radius is 2, the height is 4. And so we're looking right here. When the radius is some r, and the height is some h. We see that we have similar triangles here and here. And so we can set up the proportion big R over big H of the big triangle equals the little r over the little h. In other words, the radius is going to be 1/2 of the height, always. Now how do I know which one to solve for? Basically, we want dH dt at the end of the day. So we would like this to only have h as the variable. I want to substitute something with an h for the r, so that's how I know which of the variables to solve for. Again, I have to look at this information. I told you that if you could set this up, then you are good to go. I'm only looking for dH dt, so I really only want h to be my variable here. If I can get my r in terms of h, I can easily then change this to have one variable. Now that I've done that, taking the derivative with respect to time of both sides isn't too bad. I have pi over 12 as my constant, and then the derivative of h cubed is just 3h squared dh dt. I know dv dt is 2. I want to find dh dt when h is 3, so now that I've taken the derivative of both sides, I can go ahead and plug in my info. And I'm left with 8 over 9 pi meters per minute. So let's just review the strategy. We need to first read the problem really carefully. Draw any diagrams that we can. Introduce the notation. Assign symbols to all quantities that are functions of time. So that's what I'm doing at the beginning of the problem. I'm setting up dv dt equals what? dh dt equals what? When something equals what? Express the given information and the required rate in terms of derivatives. Write an equation that relates the various quantities of the problem. If necessary, use the geometry of the situation to eliminate one of the variables by substitution, as we just did. Use a chain rule to differentiate both sides of the equation with respect to time. Substitute the given information into the resulting equation and solve for the unknown rate. Make sure that step 7 follows step 6. A common error is to substitute the given numerical information too early. Remember, we cannot substitute, for example, in the latter problem, we couldn't substitute that x was 6 until we had taken the derivative with respect to both sides. If you do that, you'll end up seeing that you have like 0 equals 0, or you'll have some nonsense at the end that doesn't make sense. This is a very common problem, and this is probably the hardest one because people tend to get confused when we're talking about directions. But again, draw the diagram and it will all make sense. Car A is traveling west at 50 miles per hour. Car A is traveling west. A started here and it's going that way at 50 miles per hour. B is traveling north at 60 miles per hour. Both are headed for the intersection of two roads. So they're both headed for some intersection, let's call that point C, and B was headed north at 60 miles per hour. They're at some intersection. There we have our right angle. B started here and it's going up. A started here and it's going left. Let's just complete our right triangle. So probably going to want to use that geometry. At what rate are the cars approaching each other? So what are we trying to find here? Let's call this X. Let's call this Y, and let's call this Z. So we're trying to find the rate at which the two cars are approaching each other. When car A is 0.3 miles, so we're trying to find dz dt equals what? When what? When car A is 0.3 miles, so that's our x, when x is 0.3 and y is 0.4. We know that dx dt is 50 always, and dy dt is 60 always. Now, The only other thing that we need to do is we need to figure out if this is a positive 50 or a negative 50, and the same with the 60 miles per hour. So this is how we have to think. And this is where people get confused because they want to know north means positive or negative, south means positive or negative, and it's not like that. It depends on how our figure is drawn. We see over time that we are saying how far A is away. So we want to know when x equals 0.3. It's going to start at greater than 0.3, and it's going to get less and less and less over time, meaning that this rate of change should be a negative number, since my x values are getting smaller over time. Do you see that if you had drawn a diagram where A was moving away from the point C, so if A started here but it was moving away from the point C, then we would have, say that was 50 miles per hour. In this case, we would have said dx dt equals positive 50. But that's not what we're saying. We're saying that it's getting closer to our point C, so we're going to say it's negative. Similarly, B is getting closer to my point C, so my values of y are getting smaller over time. That's why this problem is difficult. So I'm just going to erase this, since that wasn't for our problem. So now we have our Pythagorean x squared plus y squared equals z squared. And now I don't have anything that stays constant, so I just have to take the derivative here and get 2x dx dt plus 2y dy dt equals 2z dz dt. I'm just going to cross all these 2's out. So I have 0.3 dx dt was negative 50 plus 0.4 dy dt was negative 60 equals, do we know what our z is? Well, we're trying to find at the moment when x is 0.3, y is 0.4. Again, we have a 3, 4, 5. So we do know what z is, but we're trying to determine dz dt. And if you do that problem, you will get negative 78 miles per hour. Now please, before you box your answer, think about it. Are the two cars getting closer together? Yes, they are. Should the sign be negative? Yes, it should. Alright, now we can box our answer and feel safe to say, I'm done. The final example says, a man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path. So it's 20 feet from the path, there's a searchlight. And it's kept focused on the man, so the searchlight is moving like that. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? So we're saying when x is 15. We are asking at what rate is the searchlight rotating? The rotation of the searchlight is theta here. So we're saying d theta dt is what? When x is 15. Now, we need to find d theta dt. We see that we have a right triangle here. What might we use? We have a theta, we have an opposite, we have an adjacent. Wouldn't it be a good idea to maybe use a tangent equation? The tangent of theta equals x over 20. And why can we put this 20 as a constant? Why is it safe to do that and not have to write y? It's safe because the searchlight is located on the ground 20 feet from the path. It's always 20 feet away. It's fixed, just like our ladder height was fixed. It was never changing. The man is moving. The x, it's not safe to put a number in there. But since this 20 is fixed, it's safe to put the number in before we take the derivative of both sides. So please understand the difference between that. Now we can go ahead and take the derivative with respect to both sides. The derivative of tangent is secant squared. However, our theta is moving over time, so we must even take the derivative of that with respect to time. When we take the derivative of this side, let's pull the 1/20th out. Isn't this the same thing as 1/20th x? So that when we take the derivative, we get 1/20th times dx dt. So now we can just substitute in what we have. We want secant squared of theta. That is the same thing as 1 over cosine squared of theta. What is cosine squared of theta when we plug in our values? So when we plug in our values, we have 15, 20, and here's theta. So we have 15, 20. Look, we have a 3, 4, 5 yet again. So they're not making that part very hard for us. So the cosine of theta here would just be adjacent over hypotenuse, 20 over 25, or 4/5. And so let's just keep with this. d theta dt is what we're trying to solve for, equals 1 over 20 dx dt. And what was dx dt? I forgot to write that down. Let's read the problem again. A man walks along a straight path at a speed of 4 feet per second. So he's going this way at 4 feet per second, meaning dx dt was 4. And so we can substitute that in. And we found that the cosine of theta was just 4/5. Just left with d theta dt equals 0.128. And what is our units here? We know it's something per second. And what is degree measures? On the AP exam, we're always going to be dealing with radians. Radians per second. In this section in particular, please, let's practice putting our units. I will take off credit for not having units, because in the AP exam, on many problems, you get 1 full point just for writing the units. That's about it for this lesson. This is one that you'll probably need to watch now, and then when we do it in class and we're reviewing for the quiz, I would definitely watch this video again. This is too much to digest just once, but I promise it's not bad once we get to know how to write the problems, read the problems, and solve the problems.